everyone, Katrina here, and today I'm going to tell you all about what eigenvalues mean. So make sure to watch to the end to see all the 4 different scenarios that we can have, and please subscribe for more videos. Okay, let's look at the first case. What happens if we have distinct eigenvalues? So given this matrix A over here, we see that we have some eigenvalue which equals to 3 and our second eigenvalue which equals to 2. And these eigenvalues have the following corresponding eigenvectors. Corresponding to eigenvalue 1 is our v1 here, and corresponding to eigenvalue 2 is our v2 over here. In this particular case, our v1 represents the x-axis and v2 represents the y-axis. In this situation, when we have distinct real eigenvalues, that means that we have a transformation that scales along the eigenvectors. So we're simply just scaling. So in particular, we see our matrix A scales along the x-axis by 3, because that corresponds to this eigenvalue over here. And then we can say that A also scales along the y-axis by 2. And that corresponds to this eigenvalue 2 over here. So this makes sense if you think about our eigenvalue-eigenvector equation. We have AV equals to lambda V, where A is our matrix, V is our eigenvector, and lambda is our eigenvalue. So when we apply matrix A to our eigenvector, it scales our eigenvector by factor of lambda. So we can see exactly here, if lambda equals to 3, then we're scaling that eigenvector by 3. And when lambda equals to 2, then we're scaling that eigenvector by 2. So there's no rotations here. We're simply either stretching or compressing along our eigenvector. Amazing. Let's go to our second case. What happens if we have complex conjugates? So complex conjugates are given in this form, where we have our lambda, our eigenvalue, equals to A plus or minus IB, where A is our real part and B is our imaginary part. So let's look at this example over here and consider matrix R. So this matrix has 2 eigenvalues. First eigenvalue over here equals to I, and the second eigenvalue equals to negative I. So as you can see, these are purely imaginary because A equals to 0. So we just have the imaginary part and not the real part. So as a result, this actually represents a 90-degree rotation in the counterclockwise direction. So our imaginary part corresponds to the rotation, whereas our real part corresponds to a scaling or to a stretch. So here, since A equals to 0, we are not scaling our values at all. We are simply just rotating them. So that is the case of a complex conjugate. We often think that eigenvalues just scale our eigenvectors. That is only the case when we consider real eigenvalues. But when we have our complex conjugates, we can see here that we actually have a rotation. So the third type of situation we can have is repeated eigenvalues with full eigenvectors. So full eigenvectors means that the number of eigenvectors equals to the dimension of our matrix A. So it has to have full rank in order to have full eigenvectors. So let's look at an example over here. So say we have some matrix A that equals to 2, 0, 0, 2. In this case, it's easy to see that our eigenvalues equal to 2. So this is a diagonal matrix, so that means that our eigenvalues here are going to be found along our diagonal. So in this case, our eigenvector can be any vector. So that is incredible because we have this specific format where we have the zeros on the non-diagonal and our eigenvalues on the diagonal. Our eigenvectors can be anything. So in this case, we actually have a full eigenvectors. So that means the number of eigenvalues equal to our dimension. And in here, our dimension equals to 2. So let's take a second and think about what is the interpretation of this. What does this actually mean? Well, this means that we have uniform scaling. And what does uniform scaling mean? That means that everything is stretched by a factor of 2. So we have a big stretch by factor of 2. And that's all that's happening here. Again, no rotation. Everything is uniformly being stretched or scaled by a factor of 2. And the reason behind this is because we have our full eigenvector space. We can have another situation where we have a repeated eigenvalues. However, they do not have a full eigenvector space. So in that case, we have to treat them a little bit differently. Let's consider our matrix A being 1, 1, 0, 1. In this case, we see that our repeated eigenvalues equal to 1. However, we have this 1 in our top right corner. So because of this, that means that we only have one eigenvector. So our eigenvector here equals to 1, 0. Since we only have one eigenvector here, we see that the number of eigenvectors equals to 1, but the dimension of A equals to 2. So these are not equal to each other, therefore we do not have full rank. So because of this, what this means is we are having a shearing. So instead of having a stretch or compression along our eigenvalues, we have a shear. So what that means is that the matrix shears our points. So the x-axis remains fixed, but the y-coordinates are shifted proportionally to x. So this shape tilts our matrix instead of just scaling it. So we can think of this as a tilt, and we can also think of this as our points being shifted proportionally towards x. So this is a different type of transformation. So this only occurs when we do not have a full rank of eigenvectors. So I hope this gives you a bit of a clearer understanding of the different types of eigenvalues that we can have and what their transformations actually mean. What is the interpretation of the different kinds of eigenvalues? So we've seen that these transformations are different depending on the type of eigenvalues, whether they're real or imaginary, and also if they are repeated or distinct. Well, I hope you enjoyed the video today. If you did, please drop a like and feel free to comment any questions that you have. I look forward to hearing from you, and please subscribe for more videos. I'll see you next time.